Next up, we have Noah Kittner, professor in environmental science and engineering and city and regional planning and E3P.
Yeah.
Guy has 3 nations, and Noah's going to be talking about his work.
Welcome, everyone. Thanks. Today I'm going to tell you a little bit about the research that my group is doing on sustainable and resilient energy. And in particular, we're thinking about what are the environmental, economic, and health impacts of fossil fuels, and what are potential solutions in the clean energy transition that work here and around the world. Our work looks at planning for low carbon, healthy, resilient energy systems. And in particular, recently we've been really focused on what are innovations in distributed energy systems like microgrids or vehicle-to-grid systems or energy storage technologies that could help achieve a more sustainable transition. Let's see. What we're doing is using a set of energy system optimization models to understand the environmental impacts of energy infrastructure decision making. For example, Melanie Elliott was involved in the study that was published where we looked at the vehicle-to-grid implications of using electric school buses in North Carolina as a source for energy storage. And what we were doing is quantifying the total amount of potential energy storage that could reduce the peak electricity demand during periods. And school buses are particularly interesting since they're parked for a large portion of the day while kids aren't at school, as opposed to regular public transit vehicles, which are constantly in operation. We're also looking at technological learning curves for energy systems, and I'll talk about that in a minute. This type of research is trying to project how quickly emerging energy technologies will fall in cost in order to make better planning decisions now about what types of technologies can lead to faster rates of decarbonization and better material usage and other environmental or health impacts. So an area that, so one of the projects that has been a big focus recently is looking at what are the existing long-duration energy storage technologies that could help meet different states' decarbonization targets. So in California, they passed a law by 2045, there needs to be net zero carbon emissions in the electricity sector, but there's not necessarily a clear path on how to get there. And some of those technologies are still under development. And so identifying which technologies from a storage perspective could use more investment and are further along that could help reduce the cost quicker would be really beneficial for government agencies and scientists trying to model what are the actual emissions reductions. We're also looking at now how affordable it is to make the transition to clean energy systems. A lot of studies have noted the deep barriers there are to actually getting clean energy technologies in households that are the most vulnerable or marginalized communities. And so from an affordability perspective as well, we've been partnering with researchers at NCA&T to establish a North Carolina household energy network that is looking at the affordability of home energy bills and then evaluating what are the costs of upgrades that are made available by things like the Inflation Reduction Act and things like that. So with regard to long-duration energy storage, you might be wondering, well, there's a lot of talk on lithium-ion batteries, so why do we need other types of storage? Well, lithium-ion batteries may have a very high round-trip efficiency, but they're pretty limited in terms of the duration of the amount of time they can discharge electricity. It's really between 2 and 4 hours. And if we transition to a grid that might have a lot more solar and wind. In the future, there might be challenges, especially in the winter, where some of you may have heard of this term of the Dunkelflaute. This is a German term for the doldrum period when there's not enough sunlight or wind in the winter to meet the electricity needs. And so there might be this seasonal discrepancy between the summer availability of solar and in the winter, and so there might need to be seasonal storage options. But also, there's increasingly a business model now for energy storage technologies that could provide resilience on the grid. So with increasing power outages and the frequency of extreme weather events, we may need some storage options that could provide 10 to 100 hours of storage to make it through those events. So my group has been looking at what are conducting different techno-economic evaluations of some of these technologies like flow batteries, mechanical gravity storage, thermal electricity storage, and hydrogen, which now is receiving a lot of subsidies from the Inflation Reduction Act, but there's still a big question about how clean different flavors of hydrogen are. So you may have heard of green hydrogen versus gray or blue hydrogen, and we use tools like life cycle assessments to quantify the greenhouse gas emissions impact of these different fuel options. So resilience is also an important part of the research that we're looking at, and so then there's also a portfolio of studies that are looking at how can you use, under different criteria and objectives and under optimization models, how can you make better planning investment decisions to either decarbonize the grid or build a more resilient grid, and especially when there's decisions to be made in terms of power plants that require water resources or may have emissions to air or greenhouse gas emissions. And so we are working with other colleagues to examine the potential benefits of distributed energy systems and the opportunity cost of investing in certain large-scale power projects. Actually, Peyton Lindigan is an undergraduate here, has been working with me on updating a learning curve model that originally we were looking at different storage technologies, and now we're looking at electrolyzers for hydrogen production, because that has become a really big question, especially with the Inflation Reduction Act. The cost of water electrolysis is still pretty high and inefficient, but if you're able to use hydrogen as a drop-in substitute in industrial sectors or in aviation for decarbonization, there could be a lot lower costs to reaching our climate targets faster. We've also been doing some projects to, as I mentioned, on this household energy equity, to look at for distributed solar or heat pumps or these other technologies that are now being subsidized at a household level. There is a big disparity on who's able to access and afford these historically, and so in collaboration with other researchers on campus, including in the Angel Shoes lab and the data-driven lab, we're looking at ways to combine more sustainable distributed energy technologies with communities that are more vulnerable within neighborhoods. So for instance, ones that might experience higher urban heat island effects could benefit more from adopting heat pumps or energy efficiency measures. So that's a pretty broad overview of some of the different projects we're working on. In general, part of the thinking is that there's a lot of research now demonstrating the greenhouse gas and health impacts of using fossil fuels and coal electricity. But my lab is really focused on what are the different solutions and if we're going to transition to different technologies, and what are the impacts of those. It's not so straightforward with subsidies for things like hydrogen or different storage technologies, and they all have different costs and benefits. And so what we're doing is taking those in systems level models to evaluate how fast are they reducing in cost, what are the emissions impacts, and what is the opportunity to provide a more sustainable energy system. So I'm very happy to answer more of your questions or collaborate with you in other areas that we're interested in doing for technology evaluation. Includes the sustainability of different materials for storage technologies, and so critical minerals might be a large issue as it comes up with different next generation batteries for the grid or electric vehicles, and also thinking about how energy storage can provide resilience for more critical infrastructure like hospitals or grids that really require a high level of reliability for electricity. So thanks for your attention, and I'm happy to answer any questions. Yeah, absolutely. I mean, so virtual power plants are really interesting. They're using connected Wi-Fi connected devices that are not physically located in the same place to act as a single electricity generating unit. So think about taking a collection of a bunch of houses that have solar on their roof together and managing them as one unit, or not just solar on their roof, but if they have solar and some shared form of battery storage, this could be a solution at a neighborhood level. And I think this is a really interesting area. I haven't specifically researched it yet, but it's definitely an area to watch because it's really important.
So actually, the similar study has, or the similar heat mapping has done in, I believe, 28 cities in US. It's organized by NOAA and I forgot the name, I'm sorry. But the similar study has done in other areas. So the real question is, how can we calibrate the particle lab sensor versus other type of sensor together, and also trying to find the indicators for or predictor for this type of data. So ideally, will be a similar study also leveraging using the satellite and imagery data, but that also depends on what day the campaign data, what day the temperature was measured, and we're trying to find the most recent or most available satellite data close to that date. So that will be something similar, but also a bit different. And also maybe for the other cities, if they have more data, including like the light exposure or other wind speed, that would be also could be a potential predictor for model in other cities.
Great. Thank you all very much.
Thanks.